Hello, BC Calc. We've got day 15 coming at you with some more chain rules. So today we're going to recap chain rules specifically as it relates just on the front page to trig derivatives. And we got a little power rule at the bottom hanging out there for fun. But let's make sure we understand and remember what the derivatives of our trig functions are. Now, remember, we're treating, in this case, each of these u's as a differentiable function of x. So when we write down what the derivative is, we'll have to account for that chain rule piece of what we've got going on here. So first and foremost, at the very top of the notes, we have that the chain rule is the following. If we have some function h of x, which is the composition of two functions, f of g of x, the derivative is just the derivative of the outside function, keep the inside part the same, times the derivative of the inside function. Okay, so that's just a quick recap of what the chain rule says in general. So then as we go down the line here, if I gave you the derivative of the function sine u, we would get cosine u times du dx, right? And we'll have that in each case if u is a differentiable function of x. Moving on to cosine. Cosine, hopefully you would have been shouting out in class negative sine u du dx. Moving on to tangent. Tangent, we've got secant squared u du dx. Why not pair cotangent with it right away? Sometimes I go through the order cosecant, secant, cotangent, right? But it's kind of nice to think about tangent and cotangent, those co-functions together to get negative cosecant squared du dx. Derivative of secant is secant tangent. And then finally, we've got our derivative of cosecant as negative cosecant cotangent, co-functions there, of course, times du dx. Last but not least, we've got the power rule at the bottom. So if we have a function u of x to the n power, we can use the power rule and bring the exponent down. Now we have 1 degree less up here to the n minus 1, and then times the derivative of that inside function, du dx. Okay, so if we're good with that, the entire next page, this is going to be a short video, guys, is chain rule practice. So most of your notes tonight is actually going to be you on your own trying these. For number one, you'll notice that we have sine of t squared versus sine squared t, which are a little bit different from one another, right? So make sure you understand the difference as you find those derivatives. And then a bunch of mostly trig derivatives with applying the chain rule. And then we've got some power rule and maybe some other special stuff happening in 5. So what I'd like you to do is try these, and then what we'll do tomorrow is I'm going to break you up into groups, and you'll talk about your results. See if you get the same answers, different answers, compare, contrast, and hopefully come to a general consensus on these derivatives using the chain rule. But one thing I will do with you in this video is that the last part of these notes involves an AP exam question all the way back to 1977. Taking it on way back, you know I was not born yet from our 1984 question the other day. So taking a look here, the initial conditions is we have a function f defined by f of x equals sine cubed x plus sine cubed of the absolute value of x. And the first thing we want to do is find the derivative for x values that are greater than 0. All right, so to get started is if x is greater than 0, we have to split this up because of the absolute value nature here. We can, for part A, say that our function f of x is sine cubed plus sine cubed. So from there, what we can do is we can combine these into the function 2 sine cubed x. And then finding the derivative f prime of x for x greater than 0, we're going to get the chain rule to apply, right? So f prime of x would be, if you want to think of this as 2 times sine x cubed, you can do that. So the derivative would be, if I bring that exponent down, we're going to get 6 times now sine x quantity squared times the derivative of the inside. So the derivative of sine is cos. Okay, and you can leave it just like this, or if you wanted to rewrite it, because we usually see sine x squared as written as sine squared x. There is your function that represents the derivative. But again, really only for x values greater than 0 that's true. So now for part B, we're going to go ahead and take a look at this for x values that are less than 0. So if I'm looking at the case when x is less than 0, if I drop the absolute value, what we would get is sine cubed x plus sine cubed of negative x. And what we have here is, if you remember that negative angle identity that we might have referenced once or twice before in the notes, sine of negative x is the same as negative sine x, and then cubing that keeps the coefficient out front negative. So what this actually becomes, this is f of x to start when x is less than 0. What this actually turns into for f of x is sine cubed minus sine cubed. So since f of x is 0 for x less than 0, well, the derivative would also be 0. So definitely a little less work there when x is negative. But we have our two pieces that we've split up according to the absolute value function. And then just maybe those negative angle identities help to determine that this will become negative sine cubed of x. All right, what does part C say? Part C says determine whether f of x is continuous at x equals 0. Justify your answer. Well, what we want to make sure is, for part C, in order to be continuous, we want to make sure that the limit from the right and the limit from the left are equal to each other, and that they also equal the function value at 0. So does the limit as x approaches 0 for f of x equal f of 0? That's the question to answer to see if it's continuous there. So let's do those left and right hand limits. The limit as x goes to 0 from the left when x is negative. Well, that's kind of easy because that's just 0, isn't it? Right, our function is f of x equals 0 there, so not so bad. And the limit as x goes to 0 from the right. So let me go back to our function. Our function from the right is 2 sine cubed. But what is sine of 0? Sine of 0 is in fact 0. So from the right, it's 0. Oh, and f of 0, by the way, is in fact 0, right? If I go back to the original function. So therefore, because the left and right hand limits match and they equal the function value there, we can say that this graph is definitely continuous at x equals 0. Okay, that's the appropriate justification that we'd want to show mathematically for continuity there. And then the last part, part D, says determine whether the derivative exists at x equals 0, and then justify your answer that way as well. So we want to make sure is that, those slopes of the tangent lines, as we approach 0 from the left and right sides, are we getting closer and closer to the same thing? So notationally, you can kind of write this as f prime of 0 from the right and f prime of 0 from the left. And let's do the easy one first. From the left, we know it's 0 because the derivative is constantly 0. From the right-hand side, we have to take our derivative, which was 6 sine squared cos x, and plug in 0. Okay, so that would be 6 times 0 times 1, but hey, that 0 in the middle makes this become 0 as well. So f prime of x does exist at x equals 0. In fact, we can conclude that f prime of 0 is 0 because the left and right hand derivatives would match. Sorry, that's a very poor 0, but my paper is not in a good place here, guys. Okay, we've got it. All right, that's it for today's video. Really short day 15, but it's mostly because you're going to go back and, like I mentioned before, you're going to do the work to practice with the chain rule on those examples. And then you'll get to talk with some people in class the next day about what you got as your answers. All right, have a great rest of your day. Let me know if you have any questions.